Well, good afternoon. What we're going to get started with today is analysis of equations of motion in a couple of alternative coordinate systems. So the problems that we worked last time were in rectangular coordinates, and that's a common thing, but it's also not uncommon for us to work in other coordinate systems as well. And so what we're going to do here is, first of all, just review the basics, which there's not actually that much crazy about this, so I guess we'll start first with normal-tangential. Okay, the normal-tangential coordinate system. Basically what you would say is that you could sum up the forces in the normal direction. Okay, so you kind of figure out what all your components are in the normal direction. And this is going to be equal to a mass of a particle times the acceleration in that normal direction. And what's interesting about the normal-tangential coordinate system is that we have an expression that we can use for that acceleration in the normal orientation. We can use v squared over rho. And because the normal tangential coordinate system is always set up so that it's, the tangential part is going to be aligned with the direction of the path, that's what the definition is of it, that is the direction of the velocity. Okay, so that's the velocity that we have there is along the path, which is in a tangential direction. All right, one thing to add on to this that is a lot of times helpful for this kind of problem, I'll remind us of this, the radius of curvature is something that we can determine if we know the equation of the path. Let's say that we know that the equation of the path is like y as a function of x, right? So let's say that's the path. All right. If we have something like that where the path is y as a function of x, then the radius of curvature can be found with 1 plus the first derivative of y with respect to x squared. This taken to the 3/2, and then all of this divided by the second derivative of y with respect to x. Okay, so this is very often a very helpful equation for us to use if we happen to already know the path along which a particle is going to be moving. All right, we can then find the radius of curvature rho and plug that radius of curvature rho into a normal tangential coordinate system like this, and we have one fewer thing that we have to worry about finding using something else. Okay, so there's that, and then in the tangential direction, all right, we just have to figure out what that acceleration is in the tangential direction. There's not actually that much more that we can use. We'd need to know, kind of what that, we'd need to have enough information to know either enough forces or that acceleration in the tangential direction. So that's about as far as we can go as far as that coordinate system. The other one is, I will say, the polar or cylindrical. Okay, which these are very related to each other. In this case, we basically have space is basically divided up into, 3 directions. Generally, we have a direction that's often called z, okay, and then positions within this coordinate system are defined not so much with x and y, okay, but they are defined with a radius and an angle. And so whenever you're looking at a particular particle, let's say this is the particle that you're looking at, it isn't uncommon for you to look at that particle and say that you have, let's say a transverse direction that you often call theta, and then a radial direction that you often call r. Okay? This is referencing the idea that you have a radius back to some other sort of axis right here, right? So this would be kind of the z-axis as well. Okay, and you have this radius that comes out here, and then, you know, so that's your radial direction. You have a transverse direction relative to that radial direction, and then you have a height term that would be z. Okay, so these are the coordinates that we're dealing with, the polar and cylindrical coordinate systems. Okay, and what we can do with this is we can sum forces along each of the directions. So for instance, in the radial direction, you can sum all those forces and you can set it equal to mass times the acceleration in that radial direction. But what's interesting about this is that we have some more information about how to know what this radial acceleration is in terms of some other coordinates. So this is just equal to mass. This goes back into chapter 12. This is equal to mass times, and we can do r double dot. This is literally the rate of change, the kind of the second derivative, I should say, of how far the radius is from the pole. Okay, but that's not the only piece that we have in that direction. We also have a centripetal term. Okay, and this is one of the things that we studied when we were looking at the kinematics of the polar system. Okay, that's the radial term that we have. Okay, we can also look at the transverse term, something like this. This is going to be equal to the mass of the particle that's moving times the acceleration in that transverse direction. And if we remember back, we also have a statement of that value in terms of r and theta and their derivatives. Okay, the first part that we had there is just basically r times theta double dot. So this is the angular acceleration times the radius gives you part of how fast something accelerates in that direction. Okay. All right, and then the other piece that we have here is called the Coriolis effect, right? The Coriolis acceleration. It is 2 times the rate of change of the radius value times the angular velocity. Okay, and if we remember back, that's basically one way to interpret that is a movement to a faster location. All right, so there's those. And then, you know, those are actually enough if you're working in the polar system. If you're working in the cylindrical system, you would also add on to this statement of the different directions. You could sum forces in the z direction. And this is going to be equal to the mass of the particle times the acceleration in the z. This one is a little bit easier because there really isn't a relationship that we have to deal with. All we got to do is just look at the second derivative of z. All right? And so we can use these equations, and sometimes there are ways that we can relate various elements of these equations together in order to find things that are interesting to us. Okay? So far so good there. There is one other thing I want to touch on before we do an example. And that thing that I want to touch on is how do you determine a couple of angles that might be important to us for a tangent line to a path that is given, okay? I wasn't real happy with how my derivation of what I'm about to do here turned out when I did it in class, and so I'm going to take a little mulligan here. So again, what we're trying to find is an angle of a path relative to the radial direction whenever you're in polar or cylindrical coordinates. And so let's set that up real quick. Let's say that I am again in some sort of a space here. It could be like XY, for instance. That's not really the main thing that I care about. Let's say that in that XY space I have some sort of a path along which a particle is moving. Let's take a radius for sort of an initial position of a particle along that path, right? So this is a radius to that point. Okay. If I draw on this picture the tangent line, that's basically kind of the direction that the particle would be moving at that point. All right, so there's a tangent line right there to that curve. If you imagine the particle moving a little ways, the way you could describe that is with two things. You could basically say it goes to a different position here, right? And one of the ways you could describe that is it goes to another point that really has kind of the same radius. So you could say that's r. But then has another itty-bitty radius that's kind of hard for me to draw, but another little tiny bit of radius that happens right there. Okay? And so that little bit more radius, at least how it's shown right now, would be dr. Okay? Well, how far did it move in that little space? Well, how far it moved is going to be related to this little bit of angle difference. Okay? And you could call that d theta. Right? And that little piece that you had left over right there is going to be r d theta. And so because this gets really, really tiny, I'm going to need to draw it bigger. Ultimately, I guess one of the things I should say that we're trying to find is we are trying to find what is this angle between the radial line that we started with and this direction of the path. If the path is not just a straight circle or whatever, where the path, the tangent line would be perpendicular, if, you know, it would be in the case of a circle, but if it's not a circle or something like that, then we can't assume that that tangent line is going to be perpendicular to the radial line. And so this little angle right here, psi, is what we are trying to find. That angle relative to the radial line. So let me actually draw all that bigger. This is a little triangle right here. Okay, I'm going to draw that triangle bigger. All right. This is a right angle right here. The length that I just said a second ago we had right here was r d theta, based on the definition of what a radian is. Up here, this is dr, and let's go ahead and keep in mind that we had this line right here, and the angle that we're trying to find is this angle right here. All right, but you can see, based on the principle of alternate interior angles being congruent with one another, that is the same angle as I would have right here. All right, so based on these things, I can just very basically use the tangent function of that angle psi, and it ends up being the opposite over the adjacent, which is just r d theta over dr. Now the thing is, in polar coordinates like this, it is more common to see an expression maybe expressed where radius is given as a function of angle. And so it's not uncommon to take this expression and rewrite it as r over dr d theta, because dr d theta is a function you could very easily, or r is very easily a function often that you can take a derivative with respect to theta. All right, so that's one of the angles that I wanted to be able to demonstrate, is this angle of the direction of the path relative to the radial direction. There is another angle that I'm interested in trying to show, and this is one that isn't in the Hibbler book, at least not that I've seen. This is for cylindrical coordinates in particular. Okay, and it has to do with when you have a path in 3D. So I'm actually going to show this here in kind of some 3D space. Okay, let's say this path in 3D, we'll just show it kind of almost like a little helix. All right, and we have an original, height of a point at one location. and then there's another height maybe at another location. All right, so this is, let's say this is a radius of r, and we're going over a very, very small little change in theta, right? So there'd be kind of this difference in theta that happened right here, d theta. Okay, we'll assume that there's a very, very tiny amount of change in r over that little movement, but there is potentially a change in height, and so you could set up a little triangle in 3D where, let's say, I don't know, let's say this is like x, y, and z, and we'll say that that little horizontal leg right there is parallel with the xy plane, and then this other piece that comes up is parallel with the z. Okay. Again, it's not hard for us to see that the length of this little piece right here is just going to be equal to rd theta. Okay, and this little piece right here is going to be equal to whatever the change is in z, which we can just say is dz. Okay, now what am I really trying to get at? Well, just like we did before, it will be helpful for us to have an angle that describes this slope of that line in this space. And so let me actually take that little triangle right there, and I'll show you the angle that we're trying to go for. So there's a little triangle, and I've already identified that the size of the bottom is just going to be rd theta, and this over here is going to be dz. The angle that I'm trying to come up with is right here, and I will just, for the lack of a better variable, I'll just name it xi. Or that might be zeta, whatever that letter is. I'll use a little Greek letter like that. All right, well, what do I do with that? Well, I take the tangent of that angle, and I say it's going to be equal to dz over r d theta. Again, assuming that theta is often our independent variable when you describe these functions, what we'll say here is that the tangent of that angle is going to be equal to 1 over r, and I'll kind of isolate that from the idea that you might be able to easily find the derivative of z with respect to theta. Okay, so these are the two relationships that are handy. The first one is handy in both polar and cylindrical type setups, and in the second case that's more specifically for cylindrical, but in either case they are useful whenever we are trying to establish free body diagrams in these kind of coordinate systems. And so we'll move on now and go ahead and get started with the example that I did when I was doing this originally. All right. We have a 2 kilogram ball, and it's sitting in a track. Okay? That little ball is being pushed by an arm that is connected to a shaft. Okay? The shaft is being held by a couple of bearings. Okay? And the movement of that shaft and the arm that's attached to it is kind of driven by this torque of 60 Newton meters that we have being applied there. You see there at the bottom. All right. The arm is free to move up and down on the shaft. You can kind of imagine the shaft might be keyed or something to where it allows that arm to move up and down freely on the shaft, but it is constrained angularly on the shaft, right? So the shaft pushes the arm around and forces the ball to move up the ramp. Okay? A couple things going on here. One is we know the height. Zero height is actually right up here. Where I have my y-axis. That's where I'm going to call height 0. So we're actually starting at a negative height. based on the equation that I'm showing right there, because if theta starts at 0, starts at a -2 meters, and then as theta moves up to 180 degrees, we move up to 0 height. All right, just to orient you with how the coordinates of this thing work. Okay, as it does that, the radius of the track relative to that center point does not remain constant. Okay, it actually changes according to this expression over here. Okay, so the radius value is changing as we move around, as theta changes, and the height is also changing as theta changes. Okay. It is set up so that once the ball reaches this point right here, okay, the arm will disengage from the ball. So you can imagine it's like maybe it runs out of length or something, and so now the arm no longer is touching the ball is free to move once it hits theta equal 180 degrees, basically. Okay? Just to kind of be clear about exactly how the ball sits in the track, the ball is set up so that the arm, where the arm contacts the ball is right at the center of mass or center of the ball, as well as, so the track itself will put a force upward on the bottom of the ball, potentially, and it will also put a force sideways where that little wall comes up, and both of those happen at the center of the ball. Yes?
If the arm was located farther up towards the top of the ball, would you have to set it? You have to also...
Okay, that's a good question. The answer to it has layers. Okay, the question was, if the arm didn't touch the ball right at the middle, would you have to account for that in some way? And the answer is, kind of twofold. One is, if you want the actual forces that are applied to the ball by the track, then where that arm hits the ball is going to have an impact on that, right? Because it could push down on the ball. Having said that, what that represents, what that could represent, is basically just an internal force, and the dynamics of how the thing works may not actually change much, right? So depending on if that matters to you, I made the problem simple by just saying the arm hits it right in the middle of the ball, and so does the edge of the track, hits it right in the middle of the ball, and we can deal with some of those other things. I guess the other factor that I am not really mentioning here is that if it's really a ball, then it is actually something that has a size and therefore has potential that it could roll. And if it's rolling, then there's a whole other factor that this is no longer really a particle. It's instead become something that's more like a rigid body, right? Let's ignore all that for right now. Let's deal with the particle case. Let's deal with the simplifying assumptions that all these forces have lines of action that pass right through the middle of the ball. All right, and it's not as if this is a frictionless track, let's say, then these are not wrong assumptions if that track is frictionless.
So is that if you wanted to introduce particle, the terminology they would use would be frictionless? Like it's not rolling? Or no?
Yeah, so if I told you it was frictionless, then there would be nothing that would make the ball want to roll, right? So that would be a nice little piece of language I could put in there that is a cue to you that you don't have to deal with the rolling of the ball. Or I could say it even more directly than that. Just say, treat the ball like a particle and don't worry about rotational effects on the ball. Okay? But those things, depending on the size of the ball, very well might be, factors that shouldn't be ignored. But for now, we will ignore them. All right. So what we're supposed to do here is we are supposed to find a few things. We're actually focusing in basically immediately before we hit this point and immediately after we hit this point. All right, so we're pushing the ball up here. At some point, the ball reaches the point where theta is equal to 180 degrees. immediately before, the arm is still engaged, and we are still in this portion of the track that's defined with r of theta and z of theta. Immediately after, we have now transitioned into a portion of the track that is no longer curved around the z-axis, right? It's no longer curving like that. It's now straight. You know, this portion right here is straight. It lies in the YZ plane, okay? But it has a curvature to it that is given with this expression up here. Z of y is equal to y squared minus y over pi, okay? And in case you're curious about that, I did set that up so that the slope winds up being continuous from the portion where it was going around the circular part of the track or the curved part of the track to the part now where it's starting to curve up. And we're looking at these 2 points, immediately before it hits that 180 degrees and then immediately after it hits the 180 degrees. Okay? All right, so let's get going with this. What do you think we should do first? All right. If you've been in classes with me before, you know that the answer to this question is often we want to draw a free body diagram. All right? So that is what I will do first, is draw a free body diagram of the ball. Okay, so I'll show that right here. All right. What I'm going to do with this is now define a few coordinate axes. Okay, we'll call upward z like this. Okay, and I'm doing this kind of generally for the cylindrical coordinate system. So here's another axis. All right, this is what I'm going to call the radial axis. And then we have our transverse axis here. Okay, and because theta is going positive, you know, sort of counterclockwise looking down, that's the direction I will call positive here. Okay? So that's my coordinate system. I'm going to define my forces applied to the ball. I'm going to define them on this coordinate system. I've got a couple that are, you know, start out being relatively easy. So first of all, I should be able to determine what the force is that pushes on the ball from the arm, okay? That force, since it just pushes directly in the back of the ball, it's going to be aligned with this transverse direction, okay? That's how that arm touches the ball, is just by pushing along that direction. The force that I have there is just going to be equal to the torque divided by the radius, okay? And one thing I should do is tell you that we are specifically focusing on this theta value of 180 degrees, okay? So if theta is equal to 180 degrees, then what is T over R? $60 Newton meters divided by what? Okay. R, okay, let me go up here. What is R at 180 degrees? 180 degrees is equal to pi radians. Do you agree with that? Okay. So this is actually equal to R at pi. Okay. And so what would that be? Okay, do you agree with that? So if I plug in pi for theta, right, 1 plus pi over pi is 2 meters, right? So where I have R equal to 180 degrees, the radius value at that point is going to be 2 meters. Okay? So I can divide this, if I'm specifically setting up this free body diagram at theta equal to 180 degrees, then this is just going to be equal to 2 meters. And that tells me that this is going to be equal to 30 newtons. Okay, that's what that force is being applied right there. All right. Cool, got one of them. What else? There's another one that's relatively easy. Okay. Okay, there will be a normal force on the ball from the track. That's not necessarily the easy one that I was thinking of, but it's one that we do need to do. So let me go ahead and I'll show that one on here. That is a force that pushes up from underneath. The problem is it's not oriented directly along the z or the theta or the r. It's not directed along any of the coordinates that are given. It kind of moves, it's going to be in the theta z plane, right? And if you look at that, since this thing is sloping up, I would guess that it would be in that theta z plane, okay, pushing up like this, where there is an angle right here that tells us how, what the orientation is of this force that's pushing, right? So let me call this F bottom. Okay. That angle that I have right there, that is an angle of this kind of normal force being pushed on the bottom of the ball relative to the z-axis. Is there any way for me to potentially express that angle, in more useful terms? Okay. Keep in mind, we just did a little bit of math a second ago, and we said that when we were looking in the z, we had this angle of zeta, and it was what? 1 over r, and I'll say this is for me r of theta, times dz d theta. Okay, which means that zeta is going to be equal to 1 over, what theta value am I trying to evaluate this at? 180 degrees. R at 180 degrees is 2 meters. Okay, and then I need to put in here, if I'm going to move that tangent, this would be the inverse tangent, right? So arc tangent of 1 over 2 meters. Now, what is dz d theta? Okay. Here is z as a function of theta, right up here. The derivative of that with respect to theta is what? Okay. Yeah, the 2 constant over here goes away, right? So I just end up with 2 theta over pi, but the theta then goes away because I'm taking a derivative, right? So it ends up 2 over pi, and actually if I get the units in there properly as well, it would be 2 meters over pi. Okay. And so if I set that up, I should be able, or if I put it in a calculator, I should be able to find what that angle actually is. So inverse tangent of 2 over 2 pi, or just 1 over pi. Okay, which gives me 17.6, we'll say 17.66 degrees. Okay, and I tell you what, that's a good thing to kind of store in my calculator somewhere. Store that. Let's store it into B. 17.657 degrees. Okay, and I'll put that right here. All right, cool. So that's an important thing that we've got, is that at this point where theta is equal to 180 degrees, I know that angle. What else do I need to have on here? The weight of the ball, right? This is not just out in the middle of nowhere, so it does have a weight that is applied right here. Okay, it is a 2 kilogram ball, which means that the weight is going to be equal to 2 kilograms times 9.81. Okay, which gives me 19.62. All right, I'm going to go ahead and store that in F. Okay, so this was in B. And this is 19.62. Is that what it is? That's in newtons, and that is stored in F.
So that triangle is it's used just to find the normal force in 3 dimensions.
Yeah, so in just a second, we're going to have to actually split this up and look at how each of the components of force, force, the total force along each direction relates to the acceleration along each direction, right? That's where we're going with it. For right now, we just need to set it up to where we identify all the things that we can. All right, we're close. What else do we have? We don't have all of our forces on here just yet. Because basically, what we have so far is weight. We have the force that the arm pushes on the ball with. We have the force being pushed on the bottom, which is basically what happens right here, right? What am I missing? The track directs the ball, right? So there's another force that goes to the side right there. And where does that show up on this diagram?
Opposite direction of the R vector.
Kind of, right? It does generally point inward, but it's not exactly along the R vector because this track isn't just located so that there's a constant radius, right? If this was a constant radius, then we could easily do that. But since it's not a constant radius, that radius value is actually moving out, and so there's a difference now between, a tangent line is not set up so that that tangent line is perpendicular to R. That's, what's that?
Is it perpendicular to the force arm?
No, because it is also radial. Okay, that question was, is it perpendicular to the force arm? Answer is no, because it is also radial. It is perpendicular to the tangent direction of the track. And that's where that other equation that we just derived a few seconds ago, remember the psi equation? Okay, the tangent of psi. Okay, it was going to be equal to R. For us, that is a function of theta, right? Over dr d theta. Okay. And what is dr d theta? Okay, in dr d theta up here, the 1 that I have right there goes away when I take that derivative. The only thing that I have left is just the theta over pi, which basically leaves me just 1 over pi times m. right? Okay. And remember that at 180 degrees, my r is equal to 2 meters, right? So what this gives me is 2 meters over 1 meter over pi. That's what my dr d theta is for my function of r in terms of theta. Okay, and so what this allows me to do is calculate, let me do it this way, psi is going to be equal to the inverse tangent of, okay, 2 over 1 over pi, right? Like this. Okay. And that gives me an angle of 80.96 degrees or so. Let me store that into C. Okay. So what does that actually give me? Well, what that gives me is how far off, I'm going to actually draw another kind of some coordinates here. What it gives me is that the force that I'm pushing on this thing with is not exactly aligned according to these coordinates. It allows me to shift them over a little bit. Okay. And this is the angle psi. According to how I defined it whenever we derived that expression. It's how far you are, the angle from your radial axis to the path, a tangent line to the path, right? That's what this is. This is a tangent line to the path. All right, and that is just equal to 80.96 degrees. All right, well, what does that do for me? Well, now I have some axes that actually help me, right? Because now the force that is being put on this piece from the side happens along this axis. All right, and I'll say that that's F from that side wall. I'll just call it F sub side. All right. Is that sufficiently messy? Let me slide this stuff down because we don't need to actually see it now. What I have on the left is my free body diagram. What do you think I might want to draw over here? How about a kinetic diagram? Okay, I'm going to draw my kinetic diagram so that I show the ball again. Okay, let me set up my axes like this, just like I had before. Okay, Z, R, and theta. Okay, and what I want to put on my kinetic diagram are my accelerations. Okay, So one of my accelerations is this. It goes along the theta. This is a sub theta. But what is a sub theta? Okay. A sub theta has two parts to it. Okay. One of the parts has to do with that you're at some radius and you have some angular acceleration. Right? What's the other part that goes along with this transverse direction theta? The other part is the Coriolis effect, right? So 2 times r dot theta dot. All right, what else do we have? All right, we have an acceleration that goes up right here. We'll just say that that's z double dot. Okay. If I want to kind of be consistent with how I wrote the last one, I could say that's a sub z, but then it's just equal to z double dot. All right. Then I have another component that's in the radial direction. And this would be a sub r. But according to the equations I reminded us of near the top of this lecture, what are those components? Okay, well, there's two components. One is r double dot. And the other component is my centripetal component. So I have minus r theta dot squared. All right. And keep in mind, I want this right at the point where theta is equal to 180 degrees, right? I'm doing these both at the same position. So when theta is equal to 180 degrees, are there any of these parameters that I happen to know? Okay. I can get there. The thing that I happen to know is I know, what is that? 150 degrees per second. What is that actually giving me? Angular velocity of the arm at that location is 150 degrees per second. It does not say it's constant. It just says that's what it is right at that point in time. Okay? So what number is that, or what parameter is that in the kinetic diagram that I just set up? Yeah, that is going to be theta dot. So I know theta dot. Okay? What are some things I might not know? R dot. Okay. Question for you. If I don't know R dot, is there a way I can find R dot with some things that I know? Okay, well, I know a function for R, I think is what you're probably saying, right? So we know a function for R is given with this thing right here, right? And if I want R dot, the process of getting there, remember R dot is dr dt. So r dot is equal to dr dt. This is going to be equal to dr d theta times d theta dt. Right? Okay. And dr d theta at this point is what? We did this just a second ago. 1 over pi, right? So what that tells me here is that r dot is equal to 1 meter over pi times theta dot. That's based on the geometry of the track. Okay. So that takes care of my r dot, which is one of the things that I need. Okay. What about r double dot? That's one of the trickier ones. Okay. Here's the thing. What is r double dot? R double dot is equal to dr dot d theta. I'm sorry, not d theta, dt. Dr dot dt. Okay. What is dr dot? Or excuse me, what is r dot? So r dot is equal to 1 over pi theta dot, right? And so if I take the derivative of that, I can use the product rule, right? So if I use the product rule here, what that ends up giving me, tell you what, I'll do the product rule on my expression up here. That way it's very general, right? So if I do the product rule on that, what it tells me is that I have d dt of dr d theta times d theta dt plus, okay, dr d theta times d dt d theta dt. Right? That's the product rule. Okay. Well, here's the interesting thing. What is this term? What is the derivative of dr d theta with respect to time? Time doesn't appear in that at all, does it? Right? Which means that term is 0. Okay? And what that allows me to do is basically say that r double dot is equal to dr d theta times theta double dot. All right, that was, a bit of a journey to get there, but, we know this, we can find dr d theta, right? That's something that we actually have already done. It's just equal to 1 meter over pi. All right, what else? So now I've got r double dot taken care of. Is there anything I'm lacking in my kinetic diagram that I need to express? Okay, z double dot, all right? So let me slide some of this stuff down so we can look at that stuff. How do I do z double dot? Okay, we kind of do it the same way, right? We've got z dot is going to be equal to dz d theta times d theta dt. Okay, what about z double dot? Product rule says this is going to be equal to d dt of dz d theta times d theta dt plus dz d theta times d dt of d theta dt. Okay, what can I do here? The derivative of dz d theta with respect to time is 0. So that whole first term becomes 0. And so z double dot becomes dz d theta times theta double dot. Okay, and what is dz d theta? Okay, it becomes 2 over pi. okay? Or if we want to put units in there, 2 meters over pi, right? Theta double dot. All right. All this stuff is, even though it's maybe kind of boring, it's very useful to us because the next step is to actually do our equations of motion. And now that we have all these things established, putting all this stuff into our equations of motion actually makes them solvable. All right? Let me see if I can do that better. Nope. All right. What direction do you want to deal with first? We have 3 choices, right? We can do our transverse, we can do our radial, we can do our height, z. Okay? What do you want to do first? What we're doing here is this. We are doing a sum of forces. I'll just start in the transverse direction here, is equal to mass times the acceleration in a transverse direction. We're going to sum our forces in a radial direction. It's going to be equal to mass times the acceleration in the radial direction. And we're going to sum forces in the z direction. And that's going to be equal to mass times the acceleration in the z direction. That'll give us a system of equations. Okay? Just start in the transverse direction. So summing forces in that transverse direction. We got one that's real easy there. It's directly along the transverse direction of 30 newtons. All right? So far, so good. What else do we have? So this is, if we want to put a heading on this, we're starting to do our equations of motion here. Okay? F bottom, does it have a component that goes along the transverse direction? Yep, it does. What direction along that? Negative or positive? Negative. Okay, so I'll subtract F bottom. Okay, but not the entire F bottom. I need only a component of it. Okay, according to what trig function? You know, relative to that 17.657 degrees, I would use a sine function to get the opposite component of that, which is what goes in that transverse direction. Okay? Any other forces I have that have, you know, a transverse component? Yeah, F side does too. F side looks like it tends to push in the positive theta direction, the positive transverse direction. So I'm going to put plus F side. But I don't want the entire F side. I only want the piece that points along that direction. All right? And to get that, I would want to use the cosine of psi. Okay? All this stuff is going to be equal to the mass. What is the mass? 2 kilograms, right? Times what? The acceleration along that direction, which is going to be r times theta double dot. R is 2 meters. And what's theta double dot? Theta double dot is one of the variables we're going to solve for, right? It's going to be a function of how hard we're pushing. All right, there's no reason that we should know that one immediately. So We'll put that in. What else? Plus 2 r dot. Okay, I had r dot down here, right? R dot is just equal to 1 meter over pi times theta dot. Okay. What's theta dot? 150 degrees per second. Okay, so I'll put that in here as, okay, 150 degrees per second. But we're probably not super happy with that. Let's put in a pi over 180 degrees so that I get that into radians. Okay, all the stuff that I have there, right, is r dot. Correct? So in here is r dot. What do I need to multiply that by? Another 150 degrees over seconds times pi over 180. All right, so my first equation that I have right there has 3 variables in it. Let's do another equation. Okay. In the radial direction, we'll go with that one next. Okay. In the radial direction is my radial, the arm that pushes on it. Does it have a radial component? No, no radial component there. The weight, does it have a radial component? Nope. Does the force from the bottom have a radial component? No, because that one lies in the theta z plane, right? The F bottom here lies in the theta z plane, so it has no radial component. So the only force I've got that has a radial component is F side. It has a negative radial component, but not the entire F side, right? There's an angle there that's associated with it. I only want the piece of this that points along that radial direction. To get that, I multiply by the sine of 80.96 degrees.
So F bottom is only in C theta plane always?
It is in this case. The reason that you know that, I guess it's a kind of a fine point here, but I showed you that the bottom of this track is basically flat, or perpendicular to the z direction, right? So the force that I've got pushing up right there is basically up, but it's also can be in it has a transverse component as well, but no radial component. If I had shown this thing sloped, that changes it. But it ends up being a similar thing to what was asked a few minutes ago. It ends up being sloped, but that would end up getting reacted against the wall over here, right? And those two components would sort of act like an internal force, and so they would sort of cancel each other, right? Easiest to think of it as the bottom of it being flat like this, and that means there's no radial component. Okay? So that's actually the only force I've got in that direction. What do I set it equal to? Okay, 2 kilograms. Okay, I need r double dot, right? R double dot way down here was dr d theta, theta double dot. Okay. And what was dr d theta? Okay, I got to go up here. Dr d theta was 1 over pi, 1 meter over pi. Okay. Times theta double dot. And that is one of the things we're trying to find. All right. Minus the radius value there is going to be 2 meters at this instant. Okay, that's coming from the second term here. Then I have theta dot squared, which is just going to be 150 degrees per second times pi over 180. Like so. All right, so now I've got two equations, still in 3 unknowns. And there's no way to reduce them just based on these two. I need to write my third equation, and that is a sum of forces in the z. Okay, so there I've got minus 19.62 newtons from the weight. Okay, and what else? Okay, I do have F bottom has a component that goes in the z, but not all of F bottom goes in the z. So I would add F bottom times, I just want the component that's adjacent to where that angle is measured, so I would put cosine 17.657 degrees. All right. Anything else, any other forces in the z direction? F side does not have a z direction component. The reason why is that it has this vertical wall right here, right? So it can point in either the transverse or the radial direction, but not in the z direction. Okay. What's this going to be equal to? 2 kilograms times z double dot. Z double dot is, where was it? Right here. 2 meters over pi times theta double dot. So now we have a system of 3 equations and 3 unknowns. All right? And that means that we can solve for our unknowns. Okay. Let me actually rearrange these a little bit so that it makes it a little bit easier. So the first one I have minus F bottom times a sine of 17.657 degrees plus F side times the cosine of 80.96 degrees. Okay. Then I'll subtract 2 kilograms times 2 meters times theta double dot. This is going to be equal to, we'll just do it this way, 4 kilograms times 1 meter over pi times 150 degrees per second times pi over 180 squared. Okay? And what am I missing? What haven't I done in that first equation? 30 newtons, right? So I have to subtract off 30 newtons. Okay, and if you haven't caught on, basically what I'm trying to do here is I'm trying to set up this equation or this system of equations to make it easy to put in a tool like the Casio. Okay, next one, I have minus f side times the sine of 80.96 degrees. Okay. I do have a theta double dot there. Okay, so I need to take off the 2 kilograms times 1 meter over pi. Theta double dot. Okay. And over on the other side, I'm going to have 4 kilogram meters. And that would actually be, for this second equation, it looks like that's actually negative. All right. Times 150 over seconds, 150 degrees per second, times pi over 180 degrees, that squared. Do I have any other constant terms there? Doesn't look like it. All right, so then my last equation, I will have a couple of constant terms there. Let me see, I will have f bottom. So f bottom times the cosine of 17.657 degrees. I will not have f side, but I will have a minus 2 kilograms times 2 meters per pi. Theta double dot. And then on the other side, I will have, I guess I won't have a constant term on the other side, so other than the 19.62 newtons. All right, ready to put it in? Oops, 2. All right, so here I've got negative sine of 17. I had 17.657, I believe, in B. All right, plus, here I have positive cosine, and I believe I had that angle stored in C. Say what? Ah. Yep, thank you. Like that, you mean. Yep, cosine here, and I believe I have that in C. Okay. Then what? Okay, down here I have minus 2 times 2. And then on the other side I've got 4 times This is just 1 over pi, right? So let's actually do it this way. We'll do, that's not a good way to do it. We'll do 4 divided by pi times 150 times pi over 180 squared minus 30. Okay. In the next row, I'll do minus the sine. I believe I had that angle in C. Yep, thank you. Y'all are keeping me straight. I appreciate it. So 0 goes in the first one, right? And I move over and I do negative sine of C. Okay, the next one I've got negative 2 over pi. And then lastly, I've got negative 4 times 150 times pi over 180 squared. All right, and then the last one, cosine of B, 0, right? I won't forget it this time. 0 in the next slot, and then in the last, or in the next slot over, I've got negative 2 times 2 divided by pi. All right, and lastly, I've got 19.62. I think I had that in F. All right. Hopefully I didn't make any key punch errors. This tells me that X, which was F bottom, is going to be equal to 26.34. Newtons. Okay. The side force is going to be 24.99. Newtons. Okay. And then my angular acceleration value, theta double dot, is going to be 4.30. And that's going to be in radians per second squared. What do you think? Question is, would it be in radians?
Yeah, I thought, but I thought you converted, so I wasn't sure.
Okay. Everywhere that I'm using theta double dot in there, you'll notice that I'm converting all my parameters around it to degrees, right? Or I'm not, excuse me, from degrees to radians. So yeah, it does end up being in radians per second squared. Okay. And one of the ways you can know that is that radians is technically unitless. And so if you plug that back into something like the theta double dot right here, what that ends up giving you is kilogram meter per second squared, which is newtons, which is good that we have newtons because that would add properly with the newtons that I have in my other terms in that sum, right? So it better be in radians per second. All right, well, so what? What have we answered so far? Okay. I answered this. What are the contact forces applied to the ball at one point, right? This is at the point right before it transitions past this point where it stops curving around this sort of helix type of shape. It's not really a helix, but it's, you know, this cylindrical coordinate shaped track, and then it's going to go up into this ramp that's got a different curve to it, right? So that's the next half of it. But what we just did is we found contact forces applied to the ball at those points. What other contact force is there besides the ones from the track? We actually already found one of them, the force coming from the arm, right? We already knew that one, 30 newtons. So we have actually found the contact forces applied to the ball before it goes there. All right, what about the acceleration vector? How do I do that? Okay, now that I know theta double dot is 4.3 radians per second squared, I can actually plug that back in to each of these expressions right here. What do I have, for instance, that I'm highlighting right here? What is this? Is this my acceleration in the transverse direction? Okay. So all I got to do there is plug it back in, and what I have if I do that, okay, go back to this mode, we have 2 times 4.3, I'll just abbreviate it with 4.3, plus 2 times, okay, 1 over pi, right, times, actually let me do it this way, 2 divided by pi times, all right, 150 times pi over 180 squared. Okay, and that gives me 12.963, all right? So my acceleration vector, usually you put in the transverse one second, so I guess I'm kind of out of order here a little bit. So I'll put that in right here, 12 point, what was it? 12.963. This would be in meter per second squared, and that would be on the unit vector a transverse direction. Okay, what about in the radial direction? Same type of idea, right? We have, let's see here, 4.3 over pi, okay, minus 2 times 150 times pi over 180 squared. So negative 12.34 meter per second squared, and that's on the unit vector radial. And in the z, let's see, 2 over pi times theta. So 2 times 4.3 divided by pi. And that would be about 2.74 or so. Easy, right? Kind of feels a lot like statics, probably. As a matter of fact, that's actually one of the ways that some people do these types of problems, is that they envision those accelerations as if they are forces, right? Sometimes that's the way some people picture these problems mentally. I don't prefer it that way personally, but that's the way a lot of people do it, and they might refer to those as actually inertial forces, and then they include them like this. I think it's better to do it like we did here, personally, but I know of people that like to think of those, the terms like my 2 kilogram times 1 meter over pi theta double dot, they think of that as an inertial force. All right. Well, we're almost done, but we have another part to do, right? What's our second part of this problem? Okay. Now we need to look at what about right after it passes that point. Okay. Excuse me. All right, if we look at right after it passes that point, we now have a very different situation. Our very different situation we have is in this YZ space. There is now a path here that is defined with this function that was up here, z of y. Okay, and actually, I try to do this, and I didn't do it this time. What would the units have to be on that, on these values? So it would actually have to be like y squared per meter, right? Why would that be if I want those units to work out properly?
That's the displacement.
Yeah, well, I need y is going to be in units of meters, and so is z. So if I have y squared, that would end up giving me like meters squared. So to make the units work out, I would need to divide by meters in the coefficient to make that happen. Philosophically, I think that this is a good thing to do, to kind of carry our units, and we get to see how they work. You might have noticed that in the problems that we've worked so far, is that I carry my units through almost everything. Almost no textbooks do that. And I think it's, personally, my opinion of that is that that's very damaging not to do that. So if I ever write a textbook, it's your job to hold me accountable, and when the publisher says, don't carry your units, that's messy, it makes the example problems longer, you tell me, stay strong, put the units in there. All right, so we've got this minus y over pi, I believe. That's what I had there. Okay? And remember, now the little ball is just immediately to the left, right, of this, of where this curve is happening. Okay? What's the radius of curvature right there? All right? We don't know yet. We've got to calculate it. Okay? So we're actually in a very different situation here. We're now in a situation where it's probably going to be best to deal with this problem with normal tangential coordinates rather than cylindrical coordinates. Okay? Almost like it was planned that way. All right, so let me go ahead and find that radius of curvature. Rho is going to be equal to 1 plus dy dx squared, all this to the 3/2 over the second derivative of y with respect to x. Okay? So what is this for our problem? Well, we're actually going to do with z and y, right? So we're going to kind of replace, tell you what, I'll go ahead and fix that. So dz dy like that. Okay. So this gives me 1 plus, what's the derivative of z with respect to y? It would give me 2y, or 2 over my. Okay. What's the derivative of the y over pi? Should be just 1 over pi. Do you agree with that? So all of that gets squared, taken to the 3/2. Now what's the second derivative? Okay. All right. And what coordinate of y should I plug in to get this radius of curvature? Right? I still have a y that lingers in there. Well, if I'm going to be really pretty much right there, but immediately to the left, my y coordinate's going to be 0. Right? Because it's basically right there where y, it's, you know, if I'm just to the left of that point, I plug in a y equals 0. All right, so let me plug these things in. So I've got 1 plus, all right. Here I've got negative 1 over pi, not that that matters so much, but negative 1 over pi squared. All right. And all of this taken to the 3/2. And divided by 2. So 0.5779 meters. All right. Well, how do we use that? Well, we need to use it now with our, again, we're going to do a free body diagram and relate it to a kinetic diagram. Okay? So what are the forces that act on the particle? On the ball? We still have weight, right? 19 point, forgot now what it was, 19.62 newtons. And now I've got this force from the track. Okay? I called it F bottom before. I'll call it F bottom again now. It's for a different part of the problem now. Okay? How does it line up? What's the angle that I should have? Okay. All right. So the way we can do that is just like we've done some of the other things. We can come up with what the slope is, right? The slope is given with this function. If we take dz dy, it's equal to 2y over m minus y over pi, 1 over pi. Okay, and we do this at y equals 0. That makes this term go away. So I have negative 1 over pi. Okay? What that gives me is the slope of the line that's perpendicular to this. All right? You curious what that value actually is? Well, if you think about this, so a slope is a rise over run, correct? So if I take, so let's say an inverse tangent of something like that, you can get an angle, right? Anyway, turns out, I won't bore you with that, but it turns out that essentially what that gives you is that same angle that you left off with. I think we had it as 17.657 degrees. All right. Any other forces that are applied to the ball? Remember, the arm disengages with the ball at this point. Any other forces that are applied to the ball? It's also straight, right, as far as it doesn't move in the, let's say, x direction, right? It's entirely in the YZ plane, right? So I'd say that that's basically all we've got. All right. Here's our tangential direction, and here's our normal direction. All right, that's our free body diagram. What should my kinetic diagram look like? All right. I could have a acceleration along the tangential direction, and I can have an acceleration along the normal direction. If I have an acceleration along the normal direction, do I have an expression for that that's different than this? Something like maybe v squared over rho. All right. Before we go too much farther, what do you think v is going to be in my v squared over rho? Okay. So the tricky part about this is that your v that you will have right there is part of it is going to come from what he just mentioned is the 150 degrees per second multiplied by the radius, right? It's basically if you're back in cylindrical coordinates, it's going to be that transverse component of velocity, right? But that's actually not all of what you have, all right? That is a component of what you will have, but you also need to take care of the z component as well, okay? So what I would say here is that this v that we have is going to be equal to the square root of 150 degrees per second times pi over 180, okay, times the radius at that point, right? The radius times theta dot gives you a linear speed, okay? So I multiply this by 2 meters is what the radius is at that point, okay? And all of this is going to be squared because that takes care of my transverse component. What is my velocity in the z? Okay, gonna go way down here. My velocity in the z is actually going to be, because remember dz d theta was equal to this 2 meters over pi, right? So z dot is going to be equal to 2 meters over pi times theta dot. Okay. And where that comes into play up here is, all right, 2 meters over pi. Theta dot is just 150 degrees per second times pi over 180. Okay, and if you want to kind of keep track of what we're doing there, the stuff I have right here, this is my transverse component, and this is my z component. And that gives me my velocity right there at that instant. All right. Square root of 150 times 150 times pi times 2 divided by 180 squared plus, all right, here I've got 2 times 150 times pi divided by pi times 180. Okay, 5.495. meter per second. Okay, which means here that my normal acceleration is going to be equal to that squared, right, over rho, 0.5779. 52.25 meter per second squared. All right, well, what do I do with that? Okay, I can sum forces here along two directions. My tangential direction, okay, if I do along my tangential direction, I will have the contribution of the weight, all right, so that'll be minus 19.62 newtons times what? The sine of 17.657 degrees. Okay, that's my only force component along that tangential direction. Therefore, I know that this is going to be equal to the mass times that tangential acceleration, which tells me that that tangential acceleration, okay, is going to be equal to minus 19.62 times the sine of 17.657 divided by 2. So negative 2.98. Meter per second squared. All right, and what we might also be interested in is a sum of forces in the normal direction. Okay, there I've got positive F bottom that's the entire portion of that, right? Minus 19.62 newtons times the cosine 17.657 degrees. And this is going to be equal to 2 kilograms times 52.25 meter per second squared. Okay, and this tells me that the force put on the bottom of the ball by the track is going to be equal to 2 times 52.25 plus 19.62 times the cosine of 17.657. $123.19 newtons. All right. Any questions? Yes. Okay, so from the point immediately before going on the ramp to the point immediately after going on the ramp, right? So basically, when I say ramp, I'm basically looking at the point immediately before, right here, point immediately after. There has been no time over which the velocity can change. Velocity doesn't like to change instantaneously. For the velocity to change instantaneously, it takes an infinite force, and that can't happen, right? So if we're looking literally the instant before and the instant after we go past that point, the velocity has to be the same. So what I did there is I found a transverse component of velocity. Imagine it like this. Like right before traveling up on this ramp, there was a velocity where it entered that ramp. Okay? One component of that velocity, this is like where it's still on the helical ramp, right? One component of that velocity is the transverse component, right, that was left off from the previous part of the problem, right? That's where we left off. And that was this term that I put down here, okay? But we also had another term that was the vertical velocity of that particle right there at that point, right? And we need both because that gives us the velocity along the tangential direction, the velocity along the path it's actually taking, right?
So are those, is that like r theta dot?
So the first term right here is r theta dot, and then I square it because I'm taking the square root of the sum of the squares of the two components that are perpendicular to one another, right? But what's inside of the parentheses is r theta dot. Over here, I used my function that related theta dot to z dot, because this right here is z dot.
So is that kind of like a r dot?
This is not so much r dot. This comes from way down here where I have z dot related to theta dot. So 2m over pi times theta dot. Okay, what that is, if you want to think of that in terms of physically what you're doing, is it is kind of like, think of it like this. The 2 meters times theta dot gives you a transverse speed in the transverse direction. The slope is 1 over pi. So you have a certain speed in the transverse direction. If you multiply that by slope, it changes it from a transverse speed into a vertical speed, right? That's the physical meaning of that equation right there. Okay? And that's how we knew to use that. All right. Any other questions? Is that a fun problem? I thought so. Hopefully you thought so too. All right, well then I will see you next week. Have fun.